in your atom, there are different ways to represent what's going on with the electrons. And it's the outer electrons that are doing the bonding. And are going to talk about bonding in our next unit. And so this is a way to represent what those electrons are doing, the valence, okay. Electron dot diagrams and orbital diagrams are diagrams that are able to describe what's happening with the valence electrons of the atom. It's the valence electrons that do the bonding, and so that is their importance, so for us to understand where they are so that we can see how it will bond. So let's look at an electron dot diagram. So the general pattern is there on the screen. Notice that you stack up two electrons on one side, and then you're going to fill one electron in each of the other sides. So imagine that your symbol is kind of like a box here, and then you're going to draw dots around. So let me give you an example of this. So oxygen is the symbol O, and it has 6 valence electrons. And so I would draw those dots, 2 together, and then you're going to split up the other ones. So 1 on each side, and then I still need to have 1 more, so I'm going to split it up that way. Okay, so why do we do it this way? That is because the 2 dots that go together, these right here, this is your s orbital. And then these right here are each of your p orbitals. Recall that there are 3 p orbitals. So we have we'll just say a p sub x orbital, p sub y, and p sub z. So the x, y, and z isn't important. You just need to know that there are 3 p orbitals. And so when you look at your oxygen atom here, we see that we have 2 electrons in and so when you look at your oxygen atom here, you see that you have 2 electrons that are in your 2s2 orbital, and then we have each of our p orbitals right here, my 2p4 orbitals here. So, and remember those electrons, they repel each other, and so they are not going to share those 3 orbitals unless they have to. So they'll each get their own orbital, and then that very last electron in oxygen, it does have to share that first p orbital. Okay, now it doesn't matter where you start this dot pattern. I usually just start it on the right hand side, but if you want to start at the top or on the left hand side or the bottom, that's fine. But it does need to go in this pattern. So 2 go together, and then you separate the dots 1 on each side. And again, it's representing your orbitals, your s and your p orbitals. All right, so let's just practice. So nitrogen is the symbol N, and I'm going to look on my periodic table. It is in the 5 family, so I need to have 5 dots or 5 electrons. So I'm going to put 2 together, and then I'm going to separate the last 3. So there is nitrogen. Let's look at chlorine. So chlorine has the symbol Cl. Looking on the periodic table, it is in family 7A, so that would be 7 electrons. Again, 2 dots going together, and then I'm going to put 1 in each orbital, and then I will have 2 share. All right, and let's look at vanadium. So vanadium has the symbol V, and all your transition elements, all your transition metals, they have 2 valence electrons. So I just write vanadium and then 2 dots together. Okay. All right, so vanadium is a transition element, and so it does have d electrons, but you never draw the d electrons as dots, only the s's and the p's. All right, let's look at orbital diagrams. So in orbital diagrams, you use arrows to show the spin of the electron in the orbital. You will always have 2 electrons per orbital. The first electron you will always draw with an up arrow or an up spin, okay? And just like I have drawn before, the electrons don't like to share. Like for example, in the p orbitals, they don't like to share. And so you'll put one electron in each p orbital before it's forced to share. You can use parentheses, you can use boxes, you can use lines to represent the orbitals, but you must label each orbital. And I'll explain what this all means with this in this element nitrogen. So nitrogen, we has the electron configuration 1s2, 2s2, 2p3. So we're going to draw an orbital diagram. So I'm going to use parentheses for my first example. So here's my 1s, here's my 2s, and I have 3p orbitals. I know this because there's 6p electrons, up to 6 that you can have, and you can put 2 electrons per orbital. Okay, so I take those 6 electrons divided by 2, I should have 3 orbitals. All right, so now I'm going to fill in my electrons using arrows. So I'm going to start off with my 1s2. You put an up arrow in first and then a down arrow, so those two. And then I'm going to do my 2s2, so an up arrow and then a down arrow. And then I have 3p electrons. So I'm going to go up, up, up. So this is called Hund's rule, where it does not share. I call it the bus rule. So in Hund's rule, it means that you put one electron in each orbital before you ever make them share. Okay, so this is nitrogen. Let's do a few more examples. All right, chlorine. So chlorine has the abbreviated electron configuration of neon. Again, you don't have to do all the orbitals. You can just go back to that last noble gas, 3s2, and then 3p5. All right, so let's draw its orbital diagram. Some people like to use boxes, so let's go ahead and use boxes for this example. So 3 s's, and then here's my p's. So remember there's 3p orbitals because there's up to 6 possible electrons in your p sublevel. So let's go ahead and draw the arrows. So I have both of my s electrons, so there's that one, and then I need to put 5 in. So again, Hund's rule says put 1 electron in each orbital before you make them share. So go back like that. So this is chlorine. So what the orbital diagram shows us is this is half full. Okay, so all the rest of them are full, but this one's half full. So it has to do with bonding. All right, let's go to vanadium. So go back to last noble gas configuration. So Ar, 4s2, and then remember that first row is 3d, and I have 3 in there. All right, so for this one, I'm just going to use a line because that's kind of another style of how to do this. And I'm also going to stylize my electrons. So there's lots of different styles, and it really, really doesn't matter. All right, let's draw these. So we have 4s, there's 1, and then there's 10 up to 10 d electrons. So I would divide that by 2, and I would draw 5, the 5d orbitals. All right, let's put our electrons in. So we have our up arrow in first, and then our down arrow in, and then we have 3d electrons. So I'm going to go 1, 2, 3. So these are my stylized arrows. If you like these, you can use them. So I've tried to use different styles. They're all accepted, so just pick away and go with it. I usually use parentheses when I'm typing just because it's easiest. But you can also just use lines, or you can use these little boxes. Just depends on how you like it. All right, so what is this showing us? This is showing us that we have 2 empty orbitals. And yes, you do have to draw the empties. So that is important. All right, what if you had an f orbital? How many orbitals would you draw? Or excuse me, an f sublevel. You would have, well, you can have up to 14 electrons in that F sublevel. So you would draw 7. 1, 2, 3, 4, 5, 6, 7. So that would be like your 4F. Okay, if you ever had to draw that. And then again, you put your electrons in as up arrows one at a time. Now, what do these arrows mean? So if it's an up arrow, this means that it is an up spin. And if it's a down arrow, then it's called a down spin. So it's just a way to describe how we can put two electrons in the same orbital and have them stay there because they're going to repel each other. And so we describe it by saying that they have an opposite spin. And that's how they're able to fit in that same space.